Okay, so this last section about trigonometry, trigonometric functions, is going to be a serious conglomeration of so much from trig. So, come with questions, write things down, maybe use post-its or highlighters to mark where you have questions. I'm sure you'll have questions. So just remember that a radian, first of all, pi radians equals 180 degrees, if you need to remember the conversion factor. 2 pi radians equals 360, whichever you want to use, it's the same. But a radian is the angle it takes to make an arc the same length of the radius on the circle. So if you have a radius of the circle and put that length r here, like if you could make it a string and wrap it around, the angle that it makes, that is 1 radian. It's called a radian because it has to do with the radius. Okay, there are other ways to define it, and actually your book defines it a slightly different way. This makes sense to me, so that's how I like to think about it. If you want to look at that explanation at the top of page 46, I challenge you to do so. Okay, so the formula for arc length in radians is different than it is in degrees. So the radian one looks like that, okay, where S is the arc length and theta is the angle in radians, and r is, of course, the radius. Now, if you just need a quick reminder on how to do that, if you did the arc length in degrees, it would be 2 pi r, because that's the circumference, but multiplied by the angle in degrees. Okay, so I'm going to call that m for the angle in degrees. Okay, so on my picture over here, I'm just going to add that. So this guy, it doesn't have to do with my formula so much, but the theta is going to be for degrees, and I'm going to call it m for measurement of the angle. But we do it at a 360 because you're using m degrees out of all 360, so it's m 360ths of the circle that you're talking about. So you're talking about m 360ths of the arc length. So if you do that and then you want to convert it to radians, well, this darn thing is in degrees, so change it into radians. All right, so 2 pi r times m over 2 pi, right? So I'm converting into radians. Cancel, cancel. So it's really the measure, but now I'm converting it to radians, so I probably should have actually put theta there because I'm converting it. Now it's in radians, and so it's just radians times theta. All right, so find the arc length of the circle with radius 3 and a central angle of theta equals 2 pi over 3. Find the arc length. So literally just plug that into the formula. S equals 2 pi over 3 times a radius of 3. Yep, in fact, the arc length is 2 pi, about 6.28 inches. I should put inches on there since it actually gave me a unit. All right, now, so this is just a picture of the unit circle for your reference. If you need it, it does have all the angles and their radian counterparts. Coordinates. Actually, a teacher once showed me a really cool way to remember the coordinates. I hope you can remember the coordinates at right on the axes, because yeah, 0, -1, 1, 0. Those should be, I think, fairly self-explanatory. If not, ask me in class because I can make it easy for you. But then they said, okay, so to get these other coordinates, and so I'm going to write them outside the boxes just to maybe show you, but we're only going to do this quadrant, because if you can get this quadrant, you can get the other ones by reflecting. This and this is just, the y value of it is negative. It's the same point, just the y value is negative. And it's the same as this point, except now the x value is negative, and this guy is the same as this guy. It's just that both values, right, or it's negative this one, but it's both values are opposite of the original one up in the first quadrant. So if you can get those first quadrant coordinates, you can get them all. But anyway, he said, oh, just show students that for your coordinates, and I'm going to write them out here, you go 1, 2, 3, 1, 2, 3. Okay, divide everything by 2 and square root all the tops. And voila, you have exactly those points. So if you can count to 3, divide everything by 2, and square root the tops, you can get exactly what those coordinates are, and then you can reflect them as needed to find the points in the other quadrants. So if you're going, well, Miss Kite, this one does not have any square roots in it at all. Well, what the heck is the square root of 1? It's just 1. So if you can do that, and just sketch a little sketch on the top of your paper, like for a quiz or a test or your AP test or whatever you're doing, that might be really helpful to you. So I just wanted to bring that up. You have this for your ref as well. All right, now this is just some reminders about unit circle trigonometry, that if we're talking about coordinates, that the coordinates x comma y actually have meaning. So sine, I should put a theta in here. Sine of theta, cosine of theta. Sine of theta is always equal to y. Cosine is equal to x. Tangent is y over x. Needs a theta. Cosecant is 1 over y, or 1 over sine. Okay. Secant is 1 over x, and cotangent is x over y. And you can use this as a little cheat sheet more than anything. Don't forget the signs of the trig functions are in each quadrant are different, and maybe you learned the little trick about all students take calculus. Everything is positive, all are positive, and then this tells us that sine is the only positive one, tangent is the only positive one, and cosine is the only positive one in that quadrant. And that's how I learned to remember it. I never memorized all 3. I just learned the little all students take calculus. All right, so this page is really mostly just for a cheat sheet to remember domain, range, periods, and what each of the main 6 trigonometric functions look like on a graph. By the way, we are always going to graph in radians. We are always going to work in radians in calculus. Formulas for calculus only work in radians. So please, if you're so used to using degrees that you practice, you have to practice because you have to use radians. Those of you in physics, you're going to get used to switching your modes back and forth, or you're going to have some issues as you'll go to physics class and get all the wrong answers, or come to calculus class and get all the wrong answers. So just be aware of that, and remember to change your mode if you're having weird answers. All right, so the question at the top asks which are even and odd. So I want to talk about that really quickly. So just remember, graphically, even functions are symmetric about the y-axis, which means they're reflections over the y-axis. So like if you look here at cosine, you can see that it is reflecting over the y-axis. It is, in fact, even. All right, as is just secant. So if you look at that, it's reflecting here over the y-axis. If here's this guy, it would be over here. It's a reflection, and there would be another one way over here for the other one. So this one also is even. All right. The other ones are all odd, and you can see that right here on sines. That graphically means that it is a rotation around the origin. So if you can imagine sine going on, you can see that this half rotated 180 degrees to be down here. It is in fact a rotation. It is odd. Same deal here. This guy down here at 1 over sine, or cosecant, if you will, this guy is rotating around the origin 180 degrees to be this guy right here, or vice versa. This guy rotates up here 180 degrees. It is odd. All right. Now, tangent, also odd. You can see that just looking at the one branch, you can definitely see that this part rotates around the origin down to here, 180 degrees. It is a 180 degree rotation about the origin. It is odd. Similarly, you'll have to notice this whole branch rotates around the origin to get to this other one. And if I can just sketch in the other part for you, you can maybe see it rotates around to be the other one. So it's odd. All right, so maybe we should talk about that a little bit with respect to how it looks with the algebraic way. All right, so I put this picture up here for you to kind of help visualize it, but we're going to talk about cosine of theta. So remember that if something, if a function is even, if I put in the opposite of x, it gets me right back to my original function. All right, so we're going to put in the opposite of theta and hope that it gives me right back to cosine of theta. So I drew this little picture showing theta on the unit circle, and remember that it has coordinates x, comma, y. All right, so if I'm talking about the opposite of theta, and I just chose a random theta, but you can do it in the first quadrant and see the same thing. So the opposite of theta would go the other direction, counterclockwise from the origin, right? You measure the other way. So that coordinate, it's a reflection of the first one. It's still x, but it will be the opposite of y. Okay, whatever y was up there, it's the opposite. And you could make that same argument no matter where you put theta. Okay? So if I'm talking cosine in a unit circle, that's just x. Okay? If I'm talking, and also if I'm talking the cosine of negative theta, it's also x over 1. If I just look at that reference triangle, I have x over 1 for cosine because adjacent over hypotenuse. So you could do that. And then if you look at the one for cosine, it is also x over 1 adjacent over hypotenuse. Adjacent over hypotenuse. So cosine of theta also equals x. So in fact, the opposite of theta, cosine of the opposite of theta, and cosine of theta end up being the exact same thing. So these are equal. Cosine of the opposite of theta does in fact equal cosine of theta. It is even. So for sine, there's a very similar argument for why it's odd, and we're not going to do tangent because it's the same idea using sine and cosine. If I put in the opposite of theta, when I do that, I should get negative y over 1. Okay, or just negative y, opposite of y, I should say. And sine of theta is just y over 1. So this is equal to the opposite of sine of theta. So if I put in the opposite of theta, I get out the opposite of the function. So if you remember what an odd function was, if I put in the opposite of x, I should get the opposite of the whole function out. Negative f of x, if you will, opposite of f of x. And that's exactly what happened. So there's a hopefully sort of quick explanation of why.